Right. Normally, uh, today we are going to discuss about the viscosity questions leading to the A levels, GCA level. First of all, I'm going to discuss about Poisson's equation. When it is Poisson's equation, normally they ask you to note down now, state the Poisson's equation and describe the terms. There what you do is you have several equations, only one equation in different way. Pi a to the power 4 delta p over 8 eta l, one method. The other method you can write it as q is equal to pi a to the power 4 p1 minus p2 divided by 8 eta l. Sometimes it can be written as q is equal to pi a to the power 4 delta p over 8 eta delta l. This is very rare, this method. But if they ask you to write one of these and describe each term. Q, when you are describing it, rate of flow of liquid through the pipe also. If you want, you can write tube or as volume, better to write. Here, internal radius must be written. Pressure difference delta P is there. If it is P1 and P2, in this equation like that, P1 initial or the first end pressure. First end pressure, second end pressure, P2. Eta coefficient of viscosity of the liquid flows through. Up to this it is enough, but better to write this. L is length of the tube or pipe. Description is like that for A levels. Never, when you go with the past paper answers, that means marking scheme answers, very old ones are concerned, this internal story, that is not there, just radius of the tube. Now it is not like that, you have to perfectly write those. Right, that is there. The second instruction I am giving for this, normally they give you the equation and ask, then you have to describe the terms only. Sometimes it happens in that way also, they don't ask you to write the equation, they give it, and according to the way I wrote, just get the idea and write. Another one, in common, not only for the Poisson's, sometimes they ask you to say, write down the Stokes law or equation. So then you can write KO65 A eta V. This is there with the last part 3 video. So then of viscosity. Then A eta V. If they ask what are the terms, describe the terms. F, viscous force against the motion of the sphere. Viscous force on the sphere, that is also enough. Sphere. Against the motion is not needed, if you can. A, radius of the sphere. Radius of the sphere. This is how you write the answers. So then, radius of the sphere, if you want, you write external within brackets. Because hollow one is given, that's not needed, this is enough. Eta, coefficient of viscosity of the liquid. We never, sometimes you might in a hurry write as a terminal velocity. Stokes law, this is not terminal velocity, we can apply even to terminal velocity. Velocity of the sphere. This is how you write the if they ask you to describe the terms. Pi is not needed. Right. Sometimes the first part of the question is totally different. They give you the equation and ask, note down, write down, or state, we can say, write down the Stokes equation and prove that it is dimensionally correct. You can use this. Sometimes they might give this. Instead of this, they might give K, A, eta, V. That is either equation, it's okay. Such situation, what you do is, you consider, then your answer is concerned, you write like this. Then this is right hand side. This is left hand side. Right? Remember, that is not to indicate there, directly write right hand side F. Dimensions of right hand side. MLT minus 2. You can write like that. This is force. If you want, note it down like that. So F equals MA. M is M. A is LT minus 2. If you want, you note down like that. That is not a, it's better for you. Then, yes, wait. I wrote the left hand side first. Left hand side. Then right hand side, the other side. Right hand side. Right hand side. They have 6 pi A eta V. Then right hand side dimension. That is, we can write dimensions of K, you can ignore, A eta V. A is radius, dimension is length. Eta is ml minus 1 t minus 1. Velocity is lt minus 2. Now, this cell cancels off. Then 1 m is there, 1 l is there, t minus 1, there you get, and velocity lt minus 1, then t minus 2. This is lt minus 1, not 2. Then you can write right hand side dimension is equal to left hand side dimension. Therefore, the equation is dimensionally correct. This is how you give the answer for that, not the. So markings, according to the marking schemes, you have to write properly. Sometimes they give the equation as F equals K A eta V. Then K is ignored. So this has, or if here you write 6 5 has no dimension. Better. Because you are proving the examiner that you know everything. We actually discussed about 3 equations. First one, Newtonian or Newton equation. The first one, F is equal to, then area A eta Then we got consider delta V over delta A. So then there was certain equation like that. First day we did that Newtonian equation. There also the right hand side, left hand side story comes. Then after that, you can consider the dimensions of each side and say each side dimensions are the same. So that is another situation. Or there are so many equations coming under this. Three equations mainly coming. Those are concerned, you have to treat as it is. Past paper questions are concerned, you should know about those equations. Otherwise, you can't do anything with that. So that is very important part. These equations are to be known in a proper way. F is equal to eta A delta V over delta X. F is equal to eta A delta V over delta X. Or sometimes it is given as eta A delta V over delta X. Sometimes this is given as F equals eta A delta V over delta L. Whatever it is, if they ask the descriptions, F is viscous force against the layer. Eta is coefficient of viscosity. A is the area or overlapping area between the two layers. Then even you write common area, that is accepted. Delta V, velocity difference. Then delta X, the perpendicular distance between the two layers. So then F, viscous force on the layer. Or just write surface. A is common area. Common area between two layers. Then delta V, velocity difference, right? Or velocity difference between two layers. But this is correct for one direction. If they are moving to the opposite direction, you have to add no. So that means velocity difference, relative velocity of the two layers. Then if they say flowing to one direction, velocity difference is enough. This is not needed. It depends on the way they give the question. Then delta L, delta V, then delta L or delta X, we can use delta V, delta X. Delta X, perpendicular, that is really needed, distance between two layers. Then those are the things we have to consider. Only 4, 1, 2, 3, 4 and 5 eta. Eta is coefficient of viscosity of the liquid. Note down. Because these are important because they are giving only 2 marks for this. out of 30. But that 2 marks is very important. Next one. Sometimes they are asking what is delta V over delta X. Then directly you have to say velocity gradient, velocity gradient between the two layers or lamina also you can see. Other things I explained, this is how according to the situation you have to wordings are to be given, you have to write the wordings or descriptions. Sometimes they ask directly. In that the previous classes videos are concerned, first one I have explained all the type of questions there. Now I'll explain the first one, Newtonian ones. The questions can be given. One was given as a layer is kept it here, and here you get another wave, and the liquid is here. Then the frictional force is or viscous force there. Tension is T. Tension is T here same. This should be then what? Normally this should be smooth pulley. These springs also must be light and inextensible. But if the questions doesn't say everything, you just write the condition and do it. So then this is mg. Normal theory, I said it. T F equals ma here. T minus mg is equal to m into 0. Why? No acceleration, going with the constant velocity. And from that, so in that class I explained that, but this is one type. Another type of question which can be given under this is there is a block. It is not directly this equation with the stocks. We'll do the questions later. Then this type of this is a certain block. Block is concerned, it has mg. There should be a r here. Normal force. But we are applying horizontally all the equation for this. Therefore, these two are even marked or not marked. If they ask you to mark all the forces on this, so if this is having a certain friction, so rough surface, smooth surface, no friction for this. If this is smooth, then here they are giving a sphere which is in a liquid, viscous liquid. And then what happened? Tension is here. Mg is downwards. What are the other forces acting there? Upthrust from the mechanics is part 3 also I discussed. Then viscous force, this is moving downwards against this. Now, when you are writing the equation for this one, it has additional force. Then F equals, we'll say it is at a particular velocity or when it is at terminal velocity, V. Then F equals ma vertically down to the sphere. Then mg minus u minus f minus t is equal to m into 0. That is 0. Why? At the terminal velocity acceleration is 0. I applied F equals ma. This equation can be written for this. U can be found, F can be, that can be found from Stokes law 6phi a eta v. U, part 3 or the last class, I explained it, how to get it. Directly you can write if the radius is known, weight of the liquid displaced by this. For that, sigma and this also to be given. Sometimes mass is concerned, directly they give the mass. Sometimes they give the radius and the density of the sphere, material of the sphere, then you can find m and do the question. But here from this, we can subject T. T is equal to this. Here, since it is smooth, actually this is just falling towards that direction according to this. Then we can find the acceleration like that. Why? Only one force is horizontally. This is moving the accelerator. Such questions are normally not given. Always they are given rough surfaces. Then there is another friction. This is F dash is the friction between on the block or between this. If they ask you to draw all the forces, you have to draw F dash on the surface also, if they ask. Otherwise, you don't want to draw this. Then here we can say F equals ma for the block. T minus F dash is equal to 0. Then F dash is equal to T. Then this T is found from there and substituted. Then you can get the answers what they are asking. Just note it down. This V is terminal velocity. Remember that. Remember, if this is smooth, only one force horizontally, these forces are not acting because we are applying F equals ma horizontally, then it is moving with and certain acceleration. Such questions normally they don't give. Now I'll explain another type. A sphere is connected to one is solid. right? Solid sphere. And it is connected with a string to another hollow sphere. Shell. Shell means, hollow sphere means having some thickness here. Internal radius A1, external radius A2 like that. That is called hollow sphere. Shell means just like an egg shell. This is very thin. Very thin. So then we don't care about the internal or external separately. External and internal are almost the same. So we are considering external one. And we'll think this is kept on the surface of a liquid. This is a heavy one. This is they may be having different radii or diameters connected with a string. Then what happens is, this is a heavy one. Therefore, it goes in and rotate like that. This also then comes and this rotates and come to a position like this. Then the solid one is heavy. Then this is the solid one. This is the shell. And there is a tension here. Initially what happened is that I explained. So therefore note it down. Now I will draw the forces exerted on this. When two spheres are there, the two spheres are, one is solid and other one is hollow. So then hollow one is here or shell. The other one is solid one. Solid. Anyhow, this has a mass. This has a mass. So we'll mark capital Mg or M2G, M1G. Actually, all are in one line, but I did not draw along the same line, can draw. Then this is M1G. If it is so, I should draw it in a different color. Otherwise, you can't understand it properly. Mg, this is M2G, this is M1G. Other than this, we'll consider their radii. Both can be the same or different. A1, A1, A2. Then there should be a tension between, or tension in the string, that is T. There should be an upthrust on spheres. This is on upthrust. So much of things to be drawn on the same diagram. U1, U2. And there is another force. When it is moving downwards with a certain velocity or terminal velocity, we'll say terminal velocity. Anyhow, there is a viscous force, F1. Here, another force, F2. Normally, mechanics, better to remember how to apply for this kind of questions. F equals ma. I will encircle the forces on each sphere. Here, on this is green one, T1, black one, F2. Only two forces upward here, U2 upwards, Mg. So we'll separate this one like this. Separate the other one like this. Now you can identify the two spheres and apply F equals ma. F equals ma for the shell. When you apply, always draw the arrow downwards because direction is needed. Shell is this. Then downward forces, M1G. Then T is also, here this T is here also there. Then M1G plus T minus U1 upwards. Minus F1 is equal to M1 into 0. Why? This is for the terminal velocity situation, velocity. When it is going with terminal velocity, this might go with the same terminal velocity, we have to assume. Because both are going together. So one is going with the terminal velocity, the other one is also going with the same velocity. Sometimes second one is not the terminal velocity, but anyhow, no acceleration, constant velocity. Then, this is 0, this is the first equation. For the second one, solid one, F equals ma, vertically down. Then we can apply M2G minus U2 minus T minus F2 is equal to M2 into 0. Again, velocity is constant or acceleration is 0. So therefore, M2G minus U2, then minus T minus F2 is equal to 0. Second one. These are written according to the mechanics. Application F equals ma. That is also mechanics. Write in the equation also from mechanics. Then after that, we have to use viscosity situations. For the solid sphere, they can give you directly the mass. Then it is easy, you can mark it there. It should be, all should be marked according to SI units. Then A1, A2 are given. Anyhow, for the first one, shell, we can write Stokes. Stokes law. F1 is equal to 6 phi A eta A1 eta V. V is the common velocity here downwards. For the solid one, we can write F2 is equal to 6 phi A2 eta V. You understood, no? F1 and F2. Then you should know other things. The tension is concerned because it should be inextensible light string. It is not given if you want, but this is not directly the mechanics question. Therefore, there is no need to write that. If you want, better to write. If they do not say about the string, assuming inextensible and light string. Therefore, the tensions are everywhere the same. Right. This is the way. Then you can substitute this one. You can find U1, U2. U1 is weight of the liquid displaced by the sphere, shell, and U2 is the solid one. That is 4 by 3 pi A1 cube. Then liquid density is sigma G. Like that you can use it. Note down. Here, I want to explain another thing. If A1 is equal to A2, A1 is equal to A2, that means we'll say both are given as A. Then remember, F1 is equal to F2. You can mark as F. Why? F1 is equal to 65A eta V. F2 also same. 65A eta V. So therefore, there is no need to mark F1, F2 instead of 1F. You have to decide it. If radii are the same, upthrust are the same. Why? Radii are the same, upthrust is the weight of liquid displaced. Displaced weight of the liquid due to solid one or hollow one are the same if the radii are the same. This is external radii, this is normal radii or external. Then you don't want to mark U1, U2 separately. You can mark it as U, here also U, because both are the same. In some cases, they can say the mass of the shell negligible. Then you don't mark this one, because it is not needed. Then according to that, you have to change the equations. Right? So this is the way. But there could be situations with more than two spheres. There could be situations more than two spheres. Then it could be all solid or all. We'll say this is hollow, this is also hollow, this is solid. Solid one turns and come to the bottom. So this may be having M1G, no, M3G, M2G, M1G. Sometimes they might say both shells are concerned in negligible masses. Then you don't get this. Now, we have to consider about tensions. Here T1, here T2. Then upthrust. Here you get upthrust as U1, here U2, here U3. Then other than that, you get another force, that is viscous force. Since when it is moving constant velocity or terminal velocity, here the viscous force is F1, here viscous force is F2, here F3. If the question says all are having the same radii, then all viscous forces are the same. All upthrust are the same. Then according to that, you have to consider. Now you should know how to separate the forces. Right? So then here on this F3 T2, so this should be separated from here. Here also like this, separated from here. This one is separated like this. Then you apply F equals MA for each one. First one, we'll say this is the first one. The first one downwards. Then you get M1G plus T1 minus U1 minus F1 is equal to M into 0. That is C, first equation. For the second one, if you apply vertically down, then if you can say me again, then you get M2G plus T2, then minus U2 minus T1 minus F2 is equal to M into 0. That is 0. Second equation. For the solid one, no third one. Then downwards again F equals MA. Then you are getting M3G minus U3 minus F3 minus T2 is equal to M3 into 0. This is M2. This is M1. But there is no need to consider that one. 0. Then there are three equations. F1, F2, F3 you can write using Stokes' law. Then note down. But remember, some cases they say they are light. That means M1, M2 doesn't come. Right? Sometimes they give all three weights. According to that, you have to adjust and mark. Right. This is actually Stokes equation applications. Again, Poisson applications can be done or that can be applied for various situations. I'll explain about a certain syringe. Syringe is used to inject certain liquid drugs into the veins. Inside that, there are, but these are not physics. Some injections are given to the muscle. Normally, anti-tetanus, that is normally injected to the muscle. Slowly it should be injected, otherwise it. But some ones are given to the vein directly. Then vein inside is having a blood pressure. So then tip of this needle, this is called needle, this is a syringe. Syringe has a piston. The piston is here. We are pushing it slowly towards this direction. This is syringe. This is needle. Just mark those, label it. Now, force is given to this. There is a force applied. Slowly continuous force is given. Normally syringe has another part like this. You're holding from there and give the pressure. But early ones are not having this part. Now, normally slowly moving towards this direction. This part is wider. Therefore, we consider normal hydrostatics there. It's just like a certain force is given due to this area is considered as A, cross-sectional area. Then pressure is FOA. If they ask you to find the pressure here, pressure due to the force given to the liquid by the syringe. Then use P equals FOA. This is applied force. A is here. Then it comes in Newton per square meter or Pascal. You can find it. This should be in newtons, this should be in square meters. Then this is a wider one and slowly moving. So therefore we consider Pascal principle, hydrostatics. That means when it is a liquid at rest, normally we are saying, we assume that it's moving slowly. Therefore, pressure everywhere in the liquid is the same. When there is a tube, hydrostatics, so in a car, hydraulic brake, there is a pump here, master pump. Then we are applying a force on this F1 using our feet. And it goes there. There is a oil there, normally we call brake oil. Then other side, there are two pistons like that to the rim or the wheel. So then it expands and stop the moving part, or the motion can be, rotation can be stopped. But there also we consider the pressure here P1, here P2, but remember everywhere the pressure. P1 is equal to P2 is equal to P. For here, we consider P1 is equal to pressure F1 divided by A1. A1 is here. This is A2. A2 is smaller normally. P2 is equal to, then P2 is equal to F2 divided by A2 here. Then force is F2, A is the cylinder is here. Sorry, piston. Then, but P1 is equal to P2. So therefore, we can say this is also P, this is also P, and equate. Like that, I want to mention that even slowly moving, Pascal theorem is concerned, everywhere the pressure is the same theory. That means if you label this as X, Y, and Z, X to Y, pressure is constant. That is equal to the pressure, it is equal to pressure due to piston. Due to piston. That means the pressure here, everywhere the pressure is the same. We'll say, if you plot a graph from A to Y, X to Y, the pressure is constant. Pressure versus length. Then up to, starting from here, up to this point, pressure is constant. After that, this is a capillary tube. So this is P1, this is P2. Then this length is simple length. Then we can apply Poisson's equation. For that, we can write Q is equal to pi inside A internal A to the power 4 pressure difference P1 minus P2 divided by A eta L. That's for the tube. Poisson's equation, when you are doing it, we should consider about that. If this is not inserted to the muscles or the vein, P2 is atmospheric pressure. This is P1 is equal to P. This pressure is equal to this. Actually, P1 is equal to P. P2 is equal to PATA. So then pressure difference up to this is drawn. It's like this, but this value is PATA. This is P. If they ask you to plot a graph, pressure versus the length, this is how it varies. Here we use the Pascal theorem and we consider it's not moving, slowly moving is volume is constant like that. Normally Pascal theorem is correct for the homogeneous liquid. Homogeneous means between particles the forces must be the same. Liquid in a state of rest. It's not flowing. That situation, pressure everywhere is the same. But you can't apply that is under hydrostatics. When it is a beaker, it's not moving like that. No, then according to the height, hydrostatic pressure is there. No? H rho g, that changes. But this is a different story. It should be not exposed to this. This can be considered as the same when it is closed, in a closed area. This is hydrostatics. Now we'll consider this is a nurse or doctor is placing this inside the vein, the blood vein. Now this is vein blood. So this is pressure P2. They might give, it is not atmospheric now. Blood has a pressure. So the blood pressure is inside they will give. P2 value will be given. Or they might say P2 is equal to a certain amount. H mercury centimeters or millimeters higher than the ATA. Then what happened to P2 value? If they say like that. Now it is inserted to the vein. Then P2 is equal to PATM plus H rho HGG. More than that. PATM is normally 76 into 10 to the power minus 2 rho HGG plus H rho HGG. If the heights are given, you could have written H is in centimeters, then you can write directly in a different way. If it is in centimeters, this H into 10 to the power minus 2 is there. That situation you can write in a different way. If H is given in, then you can say 76 plus H into 10 to the power minus 2. Then total value considered in mercury, rho Hg, G. From that you can get the value. Quickly note down. Now the vein is P2. How to get it? I explained it. Normally, Sirin, remember, sometimes they might ask the force when this is not inserted. Then you can find PATM. Here the pressure is as same as here calculated from this. Then you can find the force needed. Second situation, P2 is given, then you can calculate P1. Then P1 is the same here. According to that P1, that is, if it is inserted to the vein, it's a different way we are doing. We apply first Poisson for this and find P1. After finding P1, we say everywhere the pressure is the same according to Pascal theorem. Then here P1. F1 is unknown. The new force is applied, should be applied. A is the same. So therefore, new F1 can be used. That means when it is in the vein, you have to press with a higher force. Normally, you should get a higher force for that. Normally, you have seen nurses or doctors are taking first it's in the particular bottle, will say. After that, they break the bottle off. Sometimes those days, rubber stopper was there. Through that, they insert the needle and get the needed milliliters. After that, they raise it upwards and slowly press until the liquid comes to the end. You can't see it is metal, but you can see it's coming, one drop is coming like that, small amount. You should not press it just to eject. After that, insert into the muscle and slowly. But this is not the muscle one. This is directly injected to the vein. This type of one is concerned and we can use the Poisson equation like that even for saline. Saline is given, normally bottle is there, saline bottle, then there's a small, but only the difference is this is not horizontal or straight, but we just apply. There is a needle there also. Needle is connected here. Normally this vein is here used and they insert, or sometimes they used here. Most nowadays there's another vein here. For that normally they put a needle. And all the time when the salines are given by the doctors or the nurses, you don't want to prick this. What they do is there is a small needle. They put the needle to the patient and put a plaster and keep it like that. When you want to give it, you connect to the end. Otherwise, always you have to prick these veins. So after that, then the needle. Here again it is for the vein. So therefore blood pressure is greater. Then P2 here. P1. P1 they might give you according to the liquid that is closed. So therefore, if it is open here, there is a hole there. If it is not open, you consider slowly it's coming that P1 up to this, the height, simple H1, then P1 is equal to H1 rho saline G, saline density, up to this. Then P1 is like that. Here, no pressure. But if it is open, when this is open, that part is open, there's a hole there, then you have to add PATM also. Then H1 is equal, P1 is equal to PATM plus H1 rho G, rho saline G. Like that. If it is open only, atmospheric pressure is there. Then you use P1, P2 is known. Then you can use, sometimes they ask you to put to the needle, then just like the syringe. Here, P1, P2, we can find P2 is equal to P1 plus H rho G like that, this particular height you can consider hydrostatic pressure. If they are asking the to apply for this, you don't consider that. Well, we'll do the questions, then you can understand how it is done. In some questions, you have to apply to the blood veins, veins in the body. So, veins in the body. Actual situation I drew. But we are applying Poisson's equation. Then, but actually we can't apply. So then, if you consider, first you write in the veins when blood flows, Poisson's equation is applied. But it is incorrect due to the following reasons. Number one, this vein is, then write vein is not horizontal. When you are raising the hand or whatever, it changes. That is the first thing. We can consider second one, internal radii or internal radius varies from place to place. Due to that also we can apply. In the previous video I said about this, how it happens. Today also I'll touch it. Or we can say internal cross, or another way, right? Internal cross-sectional area is not uniform. That is also we can say instead of this. These veins are considered, those are flexible. So then, right, veins are flexible. Or we can say within brackets, you write elastic. That means it expands or contracts, that can happen. These are the main things. If you want, you can say this is not homogeneous. Blood is not homogeneous. But it is, don't write it as the first one. They may ask 2 or 3 conditions for that. Then you can, will give you the common area, cross-sectional common, or the average internal radii. Internal radius everywhere if it is a common value. Like that, then you can apply length is known. I'll explain another situation. Just try to understand. In our syllabus, those things are not mentioned anywhere. According to the experience, these things are to be considered then in the syllabus. We will go through the syllabus and see whether these things are explained there. They don't ask to teach those. Again, I'll come to the heart story. Normally, we'll consider heart like this. It has some veins like that, pump from one side, coming to the blood from another side. Sending anyhow, to pump, there should be a certain work done by the heart. That work can be found. So that is mechanics again. Work done is equal to force into displacement, Fs. We know it, no? Then after that, pressure is equal to force divided by area. F is equal to PA. Or you can, if they ask such thing, you can use it equation. Not down all those. Sometimes they might ask the force and like that you use mechanics and get the answer. Now will you consider Q? Q is equal to normal situation is concerned volume divided by or mass divided by area. That also we can use. Then using these equations, we can prove certain one. The proof is not normally needed because they give the equation. Now if you consider Q is equal to M over A, not V over A, according to the mass, then Q is equal to rate M over T. Then what happens? We can find the mass per unit, that is Q. According to volume also we can find. So then I said earlier, this is according to mass, Q is equal to V over T, according to the volume. Normally we use in isolation all V over T. Then normally they give you another equation. Work done is equal to W is equal to Q delta P. Note down that equation. Normally force is equal to PA. If you write W is equal to PA into S. S is displacement for. Now we'll consider for unit time. So displacement for unit time is S. Unit time S. So then if it is A and this is the unit time, the displacement or distance it travels, so V is equal to AS. This V is, what is this AS? V is volume for unit time. That means Q is equal to V over T. T became 1, then Q is equal to V. Then we can say this as normally, if you want later we can change to in future. They haven't given such questions yet. Here A is equal to V. Note down. Sometimes they might ask in this way. V is equal to AS, Q V over T, T is equal to 1, then Q is equal to. Yeah. Some situations they will ask, then you have to adjust yourself. Because these equations normally they give the Q is the rate. According to that, they normally give normally W is equal to Fs. So F is PA, S, A into S is, we prove that Q. So then this is Q, this is P. Normally P is the pressure difference. So therefore we can write it as QP. That means W is equal to Q delta P. P normally we consider difference, pressure difference. This is how this equation comes. They don't ask you to prove, but I shown how you get it. Then not down. In these situations, they might ask, what is the work done at the initial stage? Initial stage, Q is equal to first situation. Then work done, W1. First situation, we'll say before pumping. Then Q is there, delta P is there, and you do get the answer. W2, again, new Q, Q dash, delta P. Like that, different. Then they might ask, what is the work done by the heart? Use this equation. Q is the amount of rate of flow of blood through the vein. Q. Delta P is the pressure difference. Heart gives one pressure, the other difference is can be calculated from the other end. P1 minus P2 is delta P. And some questions, the last video or the last class, we discussed about the heart, how it happens. Normally, the pressure through this. Is concerned, this is P1, P2. I said the cholesterol can be deposited here, sometimes calcium or deposits are there. Then this varies the internal diameter and cross section. Then anyhow you can use pi a to the power 4 P1 minus P2 over A theta L. So now A reduces. A reduces due to cholesterol like that. What happened? I said, then this value Q reduces. But here the our functions are to be done in the proper way. Certain amount of blood is needed always, because the blood is giving certain oxygen to the cells. So therefore, needed amount of oxygen to be supplied, the Q must come to the new one is Q dash. Again should come to Q. For that, either we have to widen this. Widen this means expand. Or we can, one method is widen. Widen means increase A. Second one, decrease eta. Then this value decreases, Q value increases. We can't change the length. We can't change the pressure at the two ends. So therefore, what happened is, for that, the doctors are using different drugs. To this one drug, for this another drug, to reduce the eta. So then two drugs are used there. Then sometimes they ask, what is the role of coefficient of viscosity in the blood pressure changes in the body? Then you can say this only, because they are asking about the liquid, that is blood. When you reduce this, normally you have to continue this medicine. Otherwise, again I said that day, other than this, the heart attack is there or angina is there, that is just like heart attack. So then what happens is some other medicine should be introduced. Normally, these high blood pressure people, the doctors are giving another medicine, calcium deposits are there. So always try to remove the calcium intake from bloodstream. So then they are giving another medicine to pass the calcium through the urine. Right? That is also there. So much of sometimes a patient is getting 5 bloods, but combinations are there. The people say that I'm taking only 2 tablets. That means there are combination. So these two are combined together, 1 tablet. Like that. Right? So then you have to, but they ask mainly about this one. And they might ask why the people having high blood pressure should take the medicine throughout in your life until you die. Reason that we have to reduce the coefficient of viscosity, therefore always this medicine must be in the bloodstream. That is the reason we have to continue. When saline is given, I said you have seen when you visit a hospital, mainly they are using, as I told, the saline bottle like that, and I explained it. Here, that comes down due to the pressure, liquid pressure. But there are some situations, the pressure changes here. Why? Remember this one. If they ask why this method is not that much good, but everywhere still using the same bottle method. Here the situation is even all is there on without that. This hydrostatic pressure to the vein from the H dash. This is the needle. This is the level height H dash. Then this pressure is equal to, I explained it early, H dash rho saline G. But the thing is, H reduces. H dash reduces. Then the pressure changes. Then the amount of saline goes to the vein reduces. Therefore, they connect through another valve like this. There is a valve like this with a ball. So then this area they can change. So then if it is slowly moving, then the nurse comes and open this widely. Then there is a disadvantage here. This method is concerned, the pressure, the saline is pumped, reduces with the height. But it is slowly because drop by drop it goes. Now there are certain injecting machines like that. That situation, I'll sketch. There is a syringe. And after that, the syringe has a needle. Before that, there is a plastic or rubber, normally plastic tube, then needle. Understood? And here you get the piston, normally. But this piston is run using a motor. Right? There is a motor. There is a motor like that. In that motor, again, inside there is a motor, it is connected like that. And there is a pipe here, again connected to the tube, plastic tube, or the syringe. You can connect it even here. Then continuous flow can be there. This is a motor. Don't draw it. It's a new method. Here you get saline. In certain cases, you can apply Poisson for this plastic tube and needle separately and do it. When you are doing questions, you can understand it. We'll say another combined tube, composite tube. We did not consider any resistance when we were applying Poisson's law from the tube itself. Right? That means if you consider the flow of liquid towards that direction, we did not consider any resistive force. That means resistance due to the tube against this. That can happen because in veins, cholesterol is deposited. There is a resistive force against that. In water lines are concerned, inside mud is deposited. Mud is deposited, then what happens is there is a resistive force against the flow. Such situations can be there. That situation, normally, these equations are not in the syllabus, but they can give the question giving the resistance. Then note down. When a liquid flows through a tube, there could be resistive force against the flow. Then that can be given as R is equal to pressure difference. Then force is normally force divided by area is the normal one. But we can prove it again as R divided by Q. Q is the rate. Delta P, pressure difference. So then, if you consider this is P1, this is P2, then this length is L, delta P is equal to P1 minus P2. Q can be obtained using the Poisson. Pi a to the power 4, then P1 minus P2 divided by 8 eta L. Eta L. So all are given. We can find P1 minus P2. Then delta P is known. So Q is known. We can get a value. Or directly we can find this here. This is delta P, no? Then Q is equal to pi a to the power 4 delta P. This is delta P. Divided by 8 eta L. Then Q over delta P. This is taken down. Pi a to the power 4 8 eta L. Like that, in various questions, you can obtain this value using this. But resistive force differs. We'll say here R1, here R2, then total resistive force R total is equal to, for the whole tube, A, B, C, A to C. That means RAB plus RBC. This is P3. If it is exposed to the atmosphere, P3 is P80. Note down. Those equations are, in physics, they can give any type of equation by explaining. We can't say it's out of the syllabus. This equation should be given like that. We'll see there are three pipes are connected like this. 3 or 4, whatever the amount. We'll consider one tube. Wait, I'll use some other color. Such situation is given. How to do this? Normally, we know that here total Q is equal to Q1 plus Q2 plus Q3. Then this is Q. Through this Q1, this is Q2 rate, this is Q3. According to combined or composite ones, I consider this junction. When you consider this junction, according to this particular junction, Q is equal to Q1 plus Q2 plus Q3. I drew all those in the second video. Right. Note down up to this. We'll consider the resistance here is R. Here the resistance is R1. Here the resistance is R2. Here the resistance is R3. Then we can write R is equal to R is equal to delta P. Delta P is the pressure difference here, divided by Q. R1 is equal to delta P divided by Q1. R2 is equal to delta P divided by Q2. R3 is equal to delta. R3 is equal to delta P divided by Q3. Like that. First draw this. Then you can write up to this. Now, in the common equation, I'll write it here. Delta P over Q. Now, from this one, I can get capital Q. Q is equal to delta P over R. From this one, Q1 is equal to delta P over R1. From this one, Q2 is equal to delta P over R2. From this one, Q3 is equal to delta P over R3. Then what I do is I use this equation. When I use that equation, Q is equal to Q1 plus Q2 plus Q3. Q1, Q is delta P over R. Q1 is delta P over R1. Delta P is difference is the same. We actually the total, we are getting actually the total resistance here. 1 pipe is considered. So here for this also delta P is the pressure difference. Delta P is the pressure difference. But here normally you get almost the same resistance here. But if you consider all together, we are finding the common resistance, average resistance R for this part. That is R. Then R is equal to Q2. Q2 is delta P over R2. The other one delta P over R3. Delta P cancels off. 1 over R is equal to 1 over R1, 1 over R2 plus 1 over R3. You can remember this for MCQs, just like in current electricity, we find the average of resistance. That is called effective resistance. In current, effective resistance is equal to, these are considered as resistances in current electricity. This is in parallel, 1 over R is equal to 1 over R1, R2 like that. The same theory like that, but this is not current, but you can remember for MCQs like this. In our syllabus directly these resistive forces against the flow is not there. They give separately with the description. Then you have to do those. Okay. Now I'll tell you another thing. When resistive force is to be, they can give you different kind of questions. We'll say it's moving like that. Large pipe is there. Then another pipe starting from here. Another pipe. Then this pipe split into two again. Split into two. One pipe. Understood? Another pipe. And here also it can split into two or three. One, two, one pipe, second pipe, another pipe. Three. Three pipes are there. Complicated. Here I consider only two pipes. And we'll say all are connected to one place. One large, maybe one large tube, or maybe a tank like this. Maybe a tank. Just drop. Liquid comes like that, going like that, and several pipes are there. If we have only two or three like this, we'll see. These are in series, the pipes. Then resistive force, R1, R2, R3. Everything is concerned R. We can prove R is equal to R1 plus R2 plus R3. If you apply for this, R is equal to delta P over Q. That is a given equation. From this we can say delta P is difference here. Delta P is equal to RQ for the first tube, second tube, third tube. Then we are getting we'll say this is delta P1, this is delta P2, this is delta P3. Then R1 is equal to delta P1 divided by Q. We know the rate through all are the same rate. Under Poisson we said no. QAB is equal to QBC is equal to CD. All are same means it is equal to Q. If you want, I'll write like this. A, B, C, D. Then we can write QAB, I'll write it here. QAB is equal to QBC is equal to QCD. I'll consider that is equal to Q. All are the same, the value is Q. So everywhere I consider Q. Then if 2 is equal to, then R2. R2 is equal to delta P 2 divided by Q. R3 is equal to delta P3 divided by Q. Because all are the same value. From this we can get delta P1 is Q R1, delta P2 Q R2, delta P3 Q R3. For this one, I'm writing, not for this. Then total pressure, delta P for this is equal to delta P1 plus delta P2 plus delta P2 plus delta P3. Then delta P is equal to delta P, R cube. This is R1 cube. This is R2 cube. This is R3 cube. Q cancel off. Then you get R is equal to R1 plus R2 plus R3. It is just like again in the current electricity equivalent resistance in series. Those are together to get the whole thing. Now you can find this situation. If 2 are there, R1 plus R2 only. This one you didn't ask from me, delta P. If you want, you can consider this is P1. This is P2. This is P3. This is P4. If you consider like that, then we can say for AB, A to B, delta P1, P1 minus P2. BC, delta P2, P2 minus P3. Then CD, delta P3, P3 minus P4. Then in common, delta P, two ends. Delta P, A to D directly. Then P1 minus P4. This is the first equation, second equation, third equation. Shall we add all those together? 1 plus 2 plus 3. Then you get delta P1 plus delta P2 plus delta P3 is equal to P1 minus P2 plus P2 minus P3 plus P3 minus P4. This is P1 minus P2 plus P2 minus P3 plus P3 minus P4. Look at this. Then what happens? Plus P2 minus P2 cancel. Then you get P1 minus P4. P1 minus P4 is delta P. So this is delta P. Then delta P is equal to delta P1 plus delta P2 plus delta P3. This is how I got this one. This is a proof. They normally don't ask you to prove, but there could be in future because questions are getting wider and wider. Very large sections are there in questions now. Right. Now I'll come to the first drawing. So they can give you resistive forces from here. R1, R2, R3, R4, R5, R6, R7. If you consider these two are concerned, that value is equal to R8. I just gave it. That is equal to parallel 1 over R8. So R8 can be found using 1 over R8 is equal to 1 over R3 plus 1 over R4. If you consider this as R9, everything together, then you can use 1 over R9 is equal to 1 over R5 plus 1 over R6 plus 1 over R7. Understood? just like current electricity resistors. Then you have two pipes like that. One is having R8 because all together this is R9. Then these two are concerned, you can get the resistance R10. R10 is equal to R1 plus R8 because now these two are in series. If you consider this as R11 is equal to R2 plus R9. One is there, one tube like that, one tube. They are in series. So this is the method. Here you get two tubes. Then total R is concerned as R is 11 R12. So again parallel. 1 over R12 is equal to 1 over R10 plus 1 over R11. Like that you have to do. New equations are given. You have to read properly and do. Don't worry about that when you look at a new equation under these properties of matter or any section. Because you read it, you can understand. After that, you can do it. Even Stokes law is concerned, when it is moving up or down, there is a small delay at the moment. That is normally called relaxation time. Relaxation time. Relaxation time. That means it doesn't always, it is delayed from certain amount of time. We'll say it is T. When it is moving, different places you are having different time. Velocities, Vt. Different velocities. We'll say one place Vt. But we had early capital VTO, this is terminal velocity. Terminal velocity. This is a new theory. Normally we consider this moving up, then it comes to terminal velocity. From the terminal velocity, it goes up. Here in this situation, in advanced situation, it doesn't happen like that. Even terminal velocity changes. Different velocities are there. And we'll say until it comes to terminal velocity or after that, mainly after that. Then they will give you another equation for this. That means instant velocity at any time. Vt. The T is normally relaxation time. Is given by, sometimes they put capital Vt. That is, what is capital Vt? That is terminal velocity. We calculate from Vt, V is equal to 2a squared rho minus sigma g over 9, 8 eta, sorry, 9 eta from this equation. Vt can be found. Then what we know this is in the syllabus now. Then after that, this equation 1 minus E minus simple T over another T, that is sometimes we call is tau, or this one. So relaxation time I'll consider as a tau. So then if it is tau, then we can, is a Greek letter, then T over 2. When you look at this at the exam, you don't feel to do. So is there, calculation is difficult also, no? That's there. Because math students can do with the questions with those things. Actually, this is not to be given because bio students do not know this. But once they give this, you check with the 2019 question. I will discuss it again. Right. Now you can do most of the 95% like that. Past papers can be done now. Right? First you do and finish. Practicals under these 3 sections. Next section is surface tension. Will be done on one particular day because practicals are very important. But under properties of matter, practicals are not given every year. Once in 5-6 years time only it is given. All the other practicals are important. Mechanics practical, first unit practical, or mechanic practical normally comes. Then heat practical, one practical from heat, thermal physics, one practical for current electricity. Normally comes sound or light, one practical comes. That is a general procedure. Normally for each practical, in future there is another video, YouTube video may be there for each and every practical in future. Okay, that is over.